Hello, my name is Peter Boza and I work with Vision Analytical. And today we're going to be talking about additive manufacturing using metal powders. We'll be talking about some samples which are considered good, some which are considered slightly used, and some that are considered actually quite ugly. Metal powders is actually something that's being used quite a bit these days in the additive manufacturing world. There's different types of metal powders that are selection of the metal powder really is dependent on the different application. These metal powders generally are very round in nature and have a specific size, and that's a requirement, not only due to the flow pattern of the nozzle that is actually depositing the powders, but also for the compactability and deposition of the particles where the parts get fused, the metal particles get fused. As a result, because I just spoke about compactability and size, particle size and shape are techniques that are broadly used when it comes to 3D metal powders. Probably the most common size technique that's out there in the world and is also very broadly used when it comes to additive manufacturing is laser diffraction. Laser diffraction is a great technique. It's very useful. It's very high throughput and you get a significant amount of data. So you get a really good representative sampling of what you're running. And it is very, very fast and very easy to use. Image analysis has also made its way into the additive manufacturing world when it comes to 3D printing using metal powders, because as we just spoke, it's not only about size, but also the flowability and actually the compactability and deposition rates. A lot of it has to do with particle shape. If you can imagine, you want these particles to be as round as you possibly can, so they flow very easily, they flow very uniformly, and they actually deposit and compress and they sinter together very uniformly as well. So automated image analysis is a complementary technique, and it is making its way into the final test of these particles. In the case today, we're going to be talking quite a bit about dynamic image analysis. So dynamic image analysis is an automated imaging platform. It works very similar to that of laser diffraction in that it's a very high throughput analysis. We can actually measure many thousands, tens of thousands of particles in minutes. This is, again, for the same reason that laser diffraction does it. It's very important because you want to try to get good statistical assurance of what particles you're analyzing. If you can imagine, it only takes a few large fused particles to clog up an additive manufacturing nozzle as it's depositing particles. Also, if these particles are not spherical in nature, they can easily affect the quality of the final product of the part. So we'll be talking about dynamic image analysis. So talking about how we're going to actually be working with these samples, just to give you an idea of the testing protocol we're going to be using today, we're going to be using a Mastersizer 3000 from Malvern Panalytical, and connected to it is an accessory called the Hydro Insight. The Hydro Insight is a dynamic image analyzer made by Vision Analytical, and it's an accessory. What it does, it allows the end user to analyze their Mastersizer, their particles using the Mastersizer, and then at the same time with the same aliquot, it's actually plumbing it into the dynamic image analyzer, the Hydro Insight, and we're getting shape results, up to 32 different shape measurements at the same time that we're getting the results for the Mastersizer. So it's an accessory and it adds complementary shape information to what you're doing on your Mastersizer. The samples we're going to be running today is a 3/16 stainless steel sample used specifically for additive manufacturing. We have a new sample that is not been used. We have a slightly used sample, and I'll talk about that in a second. And we have a highly used sample, which is considered bad. Why would we actually want to run used and used sample? Many people that are familiar with the additive manufacturing world, there is a lot of sample or metal powder at the end when the deposition is done that is unused. It is ideal and a tremendous cost savings if the operator can actually reuse that sample. The problem with reusing that sample is sometimes, because of the fusing process, it is very possible, highly probable, that when these particles are actually reused, there can be particles that are stuck together, fused, as you can see here on the screen. This is a sample where you can actually get some particles that can clog up the nozzle and for subsequent parts that are being made. And also, if it does make it through the nozzle, it can make a weak spot on the actual part. So that's why sometimes you'll get customers that are interested in using particle size analyzers, not only to assure that the new powder that they get from their vendor is good, but also to try to see if their used powder is too used. In this case, this bad powder is an example of something that was too used, overly used, and would not work anymore. So what we're going to be looking at today primarily is first the size information. So the size information coming from the master sizer is excellent. We get very good data for new powders. We can actually see that there are some differences with the used powder. And then with the pad powder, definitely we can statistically see that in your D50 and your D90, you could definitely see some differences there. So you could definitely identify a good from a bad, basically. Just to give you an idea of an overlay, the overlay here shows that, once again, we can easily see the difference between good, bad, and this really, really bad one, right? So the good used and the bad. So once again, size, very useful when it comes to looking at and identifying as a gatekeeper here to ensure that we don't use some of these samples. They couldn't clog up the additive manufacturing machine, the 3D printing machine. So looking at the complementary nature of shape, we also have some size comparisons, and we do actually compare very well. We're looking at a volume weighted distribution here, and you can see once again similar. You can see that the bad sample, which is this red sample, definitely we're seeing some of these particles kind of veer away from being in the 20 to 30 to 40 micron range, and they're all starting to show up here on the larger size range. Again, those are these larger fused particles that are starting to come together. They're getting away from being singles, and they're actually fusing and being distorted as it goes through the melting process. These two measurements assume particles are round, and this is where particle shape becomes complementary. If we assume particles are round, as you can see, this is a 34 micron particle and this is a 34 micron particle. They're not going to flow the same, and they're not going to compact the same. But looking at a particle size analyzer that just gives you size is not going to give you all the information that you really want. So here comes particle shape. So when it comes to dynamic image analysis, we can actually see that the differences, let's say, between these two particles, 34.2 and 34.1, you can see a much greater change, much greater difference when we look at their perimeter. The equivalent circular perimeter diameter is basically making a circle based on the perimeter of a particle. So the more of a perimeter or rough edge a particle has, the larger the ECP diameter will be. So these two particles that you really couldn't tell much of a difference, assuming they're round, 34, 34, now 41 to 52, you see a much more significant difference. The other two shape measures that we're going to be going through during this presentation is going to be circularity and smoothness. Just to let you know, circularity and smoothness are what's considered a fraction measure. So a fraction measure is anything from 0 to 1, 1 being its max. So in this case, 1 being very, very round, 1 in smoothness being very, very smooth. Just to let you know, again, the fraction measures are size independent. So it doesn't care if the particle is very big or very small. The smoothness or circularity will be calculated based not on size, but on the border, basically on the perimeter of the sample. So as you can see here, again, we can see differences between the particles that are not as round versus the ones that are as round. And in smoothness, same thing. We can see that some particles are smoother in nature and some particles are not smooth in nature. So what I'll do now is I'll switch over to the software. So in the software, what I did is I opened up a TIFF image of a sample that was run. And as you can see, these are all metal powders, stainless steel metal powders. This all came from the bad run. There were some particles that were round. In this case, these round particles would be great to recycle and reuse. However, there were some significant amount of particles that were not round. These are particles that can be partially fused to other particles. during the deposition process. They can be elongated, or they can be many particles stuck together, again, due to the deposition process and the melting and sintering process. Trying to glue these particles sometimes get glued together. So again, looking at just particle size is a way to differentiate uh, the particles. And if we add a model, just assuming they're round, you can see that this would be the equivalent of a 65 micron particle, a 57.6, I'm almost a 58 micron particle. But you can see that this is a 40 micron particle and this is a 40 micron particle. So as you can imagine, if we only looked at a statistical histogram for size and assumed that if everything came out to be about somewhere in the 40s, we'd be in great shape, pardon the pun. But in this case, it's really not. In this case, what we really need to do is get a lot more information to complement size and get some shape information. Out of all the different shape parameters that we chose a few. One of them, again, we just talked earlier, was perimeter, equivalent circular perimeter. Again, as you could tell, by having the perimeter, these rough edges, now you could really accentuate the differences between a particle that is round or something that has all these different edges to it. We'll also be looking a bit at circularity. Again, the closer they get to one, the more round they are. The further away, the less round they are. And we'll look at smoothness as well. So all of this is done live in real time when we capture the information as we're running it with the master sizer. So doing a comparison live here on a PowerPoint slide, and we'll go over it in a minute in the software. We saw earlier that there are some differences when you look at the ECA diameter, equivalent circular area diameter, assuming the particles are round. But we also noted that perimeter is one way to be able to differentiate things a bit. And we have. So looking at perimeter, we can also see that this sample, that's the red sample, is the bad sample. We can see that there is definitely, by number, a larger population, and even by volume, which is more accentuated. We can actually see there's a greater number of particles that are on the larger side. And then the blue powder, you can see that even though by number you can't really tell, but by volume you can see there's a much higher fraction of particles that are greater than the green one, green being the new sample. So the green sample does have a larger population of the smaller. We'll see if it's more round than the others, but we'll see that in the blue that's partially used, we start seeing that there is start decreasing some of the percentage of particles that are in this 30 to 40 micron range, and they're starting to increase because we're getting some of those fused particles and deformed particles. And then when we actually go to the red sample here, it's a bad sample, we definitely get a lower population of particles that are similar to the virgin powder, and they're moving over to these larger, higher percentage of volume percent of presence of these larger particles. So when we look at circularity, this is actually very interesting. So circularity, again, how round the particle is, the closer to one, the closer it is to round, and the further away, the less round it is. So once again, this is a very good complement because we could see in a graphical way here that number 3, again, being the new powder. So the new powder is definitely the most round in nature. Then we can see actually the red and the blue powder, definitely you start getting a larger amount of particles that are not as round. And once again, just to let you know, circularity is a fraction measure, as is smoothness, and these measures are not dependent by size. So this is independent of size. So the particles could be larger or smaller, but the circularity is independent of size. Okay. Same thing with smoothness. So in smoothness, we can also see that the brand new sample, the third one, the green one, definitely are smoother in nature, but as you can start seeing, the blue ones start moving a bit away, smoothness, and then definitely the red ones start really going into a much lower smoothness number, which definitely is the apparent causes, because we're getting a lot of particles that are less smooth. And again, this is independent of size. So we're back to the software now, and the reason we're back to the software is because all of these graphs are very qualitative. They're very nice. They explain a nice story, and I think it's a good way to be able to get a better idea of what's going on in your sample. However, what can you do with it? Let's say in a quality control perspective. To do that, what I think we should do is do an overlay. So if we do an overlay, which we did earlier, we can actually overlay the sample and look at things such as ECA diameter, mean. We already looked at this where we actually look at the number weighted and volume weighted distributions, and we pointed out the fact that if you just look at the blue and the red, let's go back here for a second, and we just look at the used and the new, and we overlay these two by size and by mean. We could see definitely that there, especially by volume, we'll see that there's definitely greater than 50 microns. There's definitely going to be some larger particles here. So even in the new versus the slightly used, we do see there is an increase in some of the larger particles here, and we can quantify that. We can actually determine what is our particle counts greater than 50. To do that, we just basically go in here and we look at some of the run data, and we can actually determine, maybe that's our magic point. Maybe that's where we have to determine how many particles we have greater than about 55, I think is what we had said. So we can pick any value we want, and then look at the statistics, and we could see, okay, 7% of the distribution greater than 55 for the new. For the used, again, we can actually see what percentage is greater, percent greater left at 55. Oops. Oh, this is on a. So 7.4%, very close. And then we can actually look to see what that looks like. If we wanted to do it this way, we could do it graphically as well. If you look at it just by just the graphs, or I did it with a percent greater or less than, but about 7, so very close. And then there's the bad, which if we look at those, I suspect we're going to see that greater than 55, we're going to see a much larger amount. Wait, by volume. Right, so 19% by volume. So definitely that would be a good way to be able to differentiate a bad or a good from a bad, where we'd say, okay, if there are EC diameter greater than, if there is more than 9, say 5%, let's say, or 7, I think it was at 7%. If it gets much above that, we're going to have a bad sample. So the other way that we can actually do these comparisons by looking at the overlays is being able to do a comparison through a graph, through a spreadsheet. So once again, if we actually overlay the 3 runs, we can actually create a run series file, and we'll just call it something, and let me just go open that file. So when we create the run series file, we get all this information for the different overlays. And what I did is I decided to kind of massage it a little bit to point out some of the key factors, and here it is. So basically, by looking at size, looking at the bad, the used, and the new, those are the first, second, third. Definitely the bad, definitely a DV, by volume, a D90, much higher than the used and the new. And then when we look at perimeter, I think that's where we also get a very large differentiation. So looking at values between size and perimeter are very important. And then you also get some information as well on circularity, where you can actually do some comparisons and see how the particles that are newer definitely tend to be a bit smoother, and they'll also tend to be rounder. So this is actually a good way to be able to quantify, not only qualify with the graphs, but quantify the differences and set some pass-fail criteria, so you can actually run a sample, run a 3D print with these metal powders, and then with the spent sample, make sure you get a good representative sampling, run them on the master sizer with the Hydro Insight together, and you can establish some limits as to where you need to stop. Again, if you were to use some of these particles that were very bad, the ones that were considered bad by the customer, these would definitely have some problems with clogging, and also if they do not clog the nozzle, if they actually make it through, you're going to have a weak sample, weak part at the So that's all I have for this presentation. I hope you enjoyed it. I thought it was very interesting to be able to get these three samples and be able to differentiate not only with graphs, histograms, not only with size, also these different shape measures, but also be able to quantify some of the differences so you can actually use that as a pass-fail criteria for spent AM metal powders. Uh, I look forward to hearing from you. If you have any questions, please contact me at the information here, and stay tuned for more presentations and more sample results on additive manufacturing metal powders. Thank you.